Chernobyl. Imagine being inside a nuclear power plant, running a test to see what would happen if the electricity suddenly went out. This is what happened at Chernobyl reactor number 4 in Ukraine in 1986. The reactor needed pumps to keep pushing water through it for cooling, but those pumps required electricity. The plant had emergency diesel generators, but they needed several seconds to start working, so the crew wanted to know, could the turbine keep spinning after a power loss and provide electricity to the pumps during those few seconds? To carry out the test, the crew began lowering the reactor's power, but it dropped much lower than intended. To raise it again, the operators pulled out a large number of control rods. These rods act like brakes inside the reactor. They absorb neutrons and help slow down the nuclear reaction. After many of them were withdrawn, the reactor became unstable. But the test continued. When the test began, the turbine started slowing down, so the power reaching the water pumps decreased. As the flow of water dropped, more steam began forming inside the reactor. And in this type of reactor, more steam made the nuclear reaction stronger. The temperature rose, and even more steam was produced. The reactor's power began rising rapidly. At that moment, the crew pressed the emergency shutdown button. It was supposed to insert the control rods and stop the reaction. But because of a design flaw in the tips of those rods, the reactor's power increased for a few moments instead of dropping immediately. Within seconds, the power surged enormously, and the water turned into extremely high-pressure steam. Then explosions occurred, destroying reactor number 4 and exposing its radioactive core to the air. Large amounts of radioactive material were released, and contamination spread across wide areas of Europe. And so, a test of emergency systems, because of operational mistakes and design flaws, turned into the Chernobyl disaster. Challenger disaster. Imagine that a small rubber piece is responsible for stopping extremely hot gases from leaking inside a space rocket. This piece was known as an O-ring, and it was located inside the joints of the rocket boosters on the American Space Shuttle Challenger. On the morning of January 28, 1986, temperatures were extremely low, and some engineers knew that the cold could make these rings less flexible. Engineers warned before launch that the rings might not seal the joint quickly enough, but the launch decision went ahead. After the shuttle lifted off, hot gases began leaking from one of the rocket booster joints because the rubber ring did not perform as it should. As the leak continued, the gases struck the external fuel tank and weakened critical parts of the vehicle. Just 73 seconds after launch, the shuttle broke apart in the air, and the 7 astronauts on board were killed. And so, a known problem in a small rubber piece, combined with the decision to launch despite the cold and the warnings, turned into one of the most famous disasters in the history of the American space program. Japan Airlines Flight 123. Imagine a small mistake being made during the repair of an aircraft, then the aircraft continuing to fly for 7 years before that mistake turns into a disaster that kills 520 people. This is what happened to Japan Airlines Flight 123 in 1985. 7 years before the accident, the aircraft's tail struck the runway during landing, damaging a metal bulkhead inside the rear of the aircraft known as the pressure bulkhead. The job of this bulkhead is to keep cabin pressure inside the passenger compartment and prevent it from reaching parts of the tail. The bulkhead was repaired, but the repair was done incorrectly. The joint was supposed to be secured with 2 rows of rivets, but part of it was installed in a way that left only 1 row carrying the pressure. With every flight, the bulkhead expanded and contracted because of changes in cabin pressure. Small cracks began to form and gradually grew larger. After thousands of flights, the bulkhead suddenly failed during Flight 123. Air rushed violently into the rear of the aircraft, tearing away a large part of the tail and severing the hydraulic lines that controlled the flight surfaces. Suddenly, the pilots lost the normal ability to control the aircraft. The crew kept trying to control it for more than half an hour, but the plane eventually crashed into a mountain in Japan. There were 524 people on board. Only 4 survived. 520 people were killed. And so, a small mistake during a repair process, hidden for years, became the deadliest single aircraft accident in history. Hyatt Regency Hotel collapse. Imagine changing one small detail in the design of a metal support system, doubling the force on a single connection point, and then watching it collapse onto a crowd of people. This is what happened at the Hyatt Regency Hotel in Kansas City in 1981. Inside the hotel's atrium, there were suspended walkways hanging above the area where people gathered. They connected different floors across the open space below. In the original design, one long steel rod was supposed to run from the ceiling through the upper walkway and then down to the walkway beneath it. But during construction, the design was changed to use 2 separate rods. The first rod supported the upper walkway from the ceiling. The second rod suspended the lower walkway from the upper walkway itself. And this is where the problem appeared. This change forced the connection point on the upper walkway to carry the weight of both walkways together. In other words, it was carrying nearly twice the load intended in the original design. On the night of July 17, 1981, hundreds of people were inside the hotel atrium during a dance event. With people standing on the walkways, the metal connections suddenly failed. The 2 walkways collapsed and fell onto the crowd below. 114 people were killed, and more than 200 others were injured. And so, a small change in the way the walkways were suspended doubled the load on a single connection point and turned into one of the worst structural collapse disasters in United States history. Mars Climate Orbiter. Imagine sending a spacecraft to Mars, then losing it because one team used a different unit of measurement than another team. This is what happened to NASA's Mars Climate Orbiter in 1999. During the journey, small thrusters on the spacecraft fired from time to time to adjust its direction and trajectory with precision. But the team that built part of the navigation system calculated the force of these thrusters using an American unit called pound force seconds. Meanwhile, NASA's navigation system expected to receive the numbers in Newton seconds, the metric unit. And that was the problem. 1 pound force is equal to about 4.45 newtons, meaning the numbers sent to the system were being interpreted as values more than 4 times different. Because the error was repeated during course correction maneuvers, the spacecraft's calculated position gradually began to differ from its real position. When it arrived at Mars, it was supposed to pass at an altitude of about 140 kilometers, but instead, it entered at an estimated altitude of only about 57 kilometers. That was far too low. The spacecraft flew too deep into the Martian atmosphere. Contact with it was completely lost, and NASA was never able to recover it. And so, the mistake was not in the rocket or the engines. It was in the failure to use one unified unit of measurement, which changed the path of an entire spacecraft and caused it to disappear at Mars.